I was just about to say that I'm delighted to moderate a climate change and environmental monitoring session. We have 8 talks today, divided by a convenient coffee break in between. Questions will be asked at the end of each block of 4. And I think also, considering the fact that we started a bit later than expected, it may make sense to jump into the session immediately. Not before actually introducing myself. I'm Carlo Bontempo. I'm the director of the Climate Change Service of Copernicus at the European Centre for Medium Range Weather Forecast. And also because of my role, I'm really delighted to be chairing and moderating this session. So our first speaker this afternoon is Karina Monchukman. Karina is an oceanographer specialized in ocean climate monitoring, working at Mercator Océan International in Toulouse. She's a member of the European Academy of Science, and she's also been one of the lead author of the most recent report of the IPCC. So it's quite hard to find a better speaker to be talking about monitoring the Arctic and Antarctic ocean climate, the Copernicus Marine Ocean Climate Indicator and Trends. So without further ado, I leave the floor to you.
Thank you very much. Thank you very much for the introduction, and welcome everybody to this presentation on the Ocean Science Data and Service. Sorry, this is a wrong presentation. Sorry, could you have downloaded the wrong presentation, I'm sorry. Is it possible to send you another presentation? No?
Maybe you can present yourself if you can.
Yes, so I've just sent you the link to the presentation. So my name is Karina Monchukman. I'm working at Mercator Ocean, and I'm definitely working on the ocean and climate activities. In particular, I'm leading the Ocean State Report activities. And so the presentation I wanted to give today is about the different results we have obtained, particularly in the most recent report of the Copernicus Ocean State Report. So I can maybe slowly start to introduce the Ocean State Report activity. So the Ocean State Report activity is one critical component of the so-called ocean reporting activities of the Copernicus Marine Service, which is covering different reporting on the blue, white, and green aspects that introduced earlier in this presentation for the variability and change in the ocean, and which is covering also European regional seas and also aspects of the global ocean. And also we have many specific topics on the Arctic area. So what we also have is so-called on this activity and the reporting is this peer-reviewed report, which is based on scientific evaluation in collaboration with more than 150 authors from Europe. And second, we have also contributions from the I just start to try to share my screen if this is possible. Can you see my slides?
Yeah, we can see your slides.
I apologize for this. So I wanted to provide an impact on the monitoring of the Arctic and Antarctic ocean climate, so the Copernicus Marine Ocean Climate Indicators and Trends. So I wanted to provide a particular starting point is that the Arctic and the polar areas, which are hosting different specific climate-related sensitive areas, particularly, for example, if we have often heard about the Arctic amplification, which is linked to an accelerated, as compared to the global average, increase of warming in this area. And also the Arctic, or the Antarctic and the Arctic area are hosting climate tipping points, such as in the Arctic area on the sea ice components, and the Antarctic areas on the Greenland ice sheet, on the ice sheets in the Arctic area, and linked also with danger to sea level rise aspects. So also for the the specific focus in the Arctic area, the shrinking cryosphere in the Arctic has led to negative impacts on food security, water resources, water quality, livelihoods, health and well-being, infrastructure, transportation, tourism and recreation, as well as culture of human societies. So this is the big messages from the Working Group 2 report, which had been just recently published for IPCC. And for the Working Group 1 report published last year is with the big message that the recent late summer Arctic sea ice area was smaller than at any time in at least the past 1,000 years and is projected to continue. So the Copernicus Marine Service, I will not go in further detail, losing already a bit of time, but is providing an access to data on ocean products, which is user-driven, backbound by user program uptake, program activities, and champion user advisory groups with the ocean products, the ocean monitoring indicators, the state report as already introduced, and the ocean visualization, which will be shown later after this second coffee break. Then with the different services on the blue markets, use cases, etc., in the user corner. So as mentioned earlier, there are also specific products with focus on the polar areas. Here again, a specific focus on the blue component with information which can lead from 1 to 25 kilometers resolution, hourly, daily, monthly, and mean averages, and even forecasting products for different aspects like sea ice concentration, sea ice thickness, sea ice velocity, and also snow, for example. Again, as I already mentioned, is the Copernicus ocean reporting activity with the core elements of the Ocean State Report, peer review with scientific credibility from more than 150 European authors, and with a summary for policymakers in collaboration with the ocean communication, marketing, and the dissemination of ocean monitoring indicators. And so with the aim to track the marine environment and evolution, but also to address a wide range of audience. So this is an example here provided on the reporting for the White Ocean for the Arctic sea ice extent. On the right-hand side, you can see the time series as part of the ocean monitoring indicator activity. And on the left-hand side, it is a figure already shown, which will be published next week, for the 6th issue of the Copernicus Ocean State Report, with a steady decline of sea ice extent, which is a serious challenge facing the Arctic. And the results for this recent report show the severe decline of sea ice in the recent years. Another highlight from the most recent report, again published next week, is the Oceanic response of the 2020 Siberian heat wave. So authors here have a specific focus on the oceanic reaction of this extreme event. And on the upper side, you can see the climatology value of a normal ice-free time between August and September in blue, and in red you can see what has happened in 2020 in reply to the Siberian heat wave, meaning that there was an extended period of ice-free area in this gray area here of the lab to sea. Then, for example, for the Baltic Sea sea ice extent, still seen in terms of a cryosphere component, which had a reporting on the record high heat content, which is strongly tightly linked to low ice extent in the Baltic Sea during winter 2009-2020. And so you can see on the left-hand side the strong interplay between the changes in ocean heat content for the last years, for example, since 2012, which is shown here as an orange line, together with the reaction in terms of the ice extent and the ice volume, which has decreased over the same period. And they have also provided a link to very long time series back to 70th century with the message that this Baltic sea ice extent in winter 2019-20 was really lowest since records they have shown for 70-20. Then there's another example again from the ocean monitoring indicator activities on the Arctic sea ice extent. Like in the Arctic and Antarctic sea ice in the Southern Ocean plays an essential role in regulating the global climate and the polar marine systems. And changes in the sea ice extent could affect these key parameters, impacting the circulation and the physics of global ocean currents. So results here for the Antarctic area included that the last quarter of the years 2017 and 2018 experienced unusual losses of ice. This has been a report from Ocean State Report 4. From Ocean State Report 5, there was a despite alarming ocean warming, which contributed to ice sheet melt. The sea ice extent in 2020 remained relatively stable. And for the most recent one, that in 22, the Antarctic summer sea ice extent minimum reached a record low, ranging the second after on the 44-year data record. Then another example for the Antarctic area on the most recent report is a focus on the marginal ice zone. So you have seen here a photo of how this looks like, which is really the transition zone between the open ocean and the dense ice drifts, where the ice covers 15 to 80% of total area of the ocean. So it's a very sensitive area, particularly for polar ecosystems and also fundamental for climate dynamics. And the results have shown that if you average over the entire Antarctic, that there is no trend in these marginal ice zones, but they have also shown with this regional data that there are some specific areas where there's a strong trend in terms of changing conditions in these marginal ice zones, which are linked also to the warming conditions in this area. So there are some takeaways. So the Arctic is subject to unprecedented change from global warming with adverse implications for the environment, society, and the economy. And the Antarctic is hosting critical climate tipping points and experienced unusual change recently, which affect polar ecosystems. The Copernicus Marine Service offers a wide range of products in its catalog for monitoring the Arctic and the Antarctic ocean climate. And it's also reporting provided access to key climate indicators and science-based knowledge, critical for polar climate. And there are upcoming new products in the pipeline, such as albedo, ice type, iceberg density, and new indicators, which will be made available in the very short term and midterm. Thank you very much, and my apologies again.
Thank you. Thank you very much, and thank you for finding a solution to a challenging problem. It's not easy to jump and solve it. Very professional. Thank you. Thank you, Karina. We'll have some Q&A at the end. I've been told that Jason Box, who is our next speaker, may have some connection issues. So let me check with whether Jason is online. Jason, can you hear me?
It's loud and clear. I think I'm ready.
Fantastic. So let me introduce you, and then I'll give you the floor, if that's okay. So Jason Erik Box is a professor in glaciology and climate at the Geological Surveys of Denmark and Greenland. He's from the US originally, and he moved to Europe for this job somehow. Over his career, has installed over 40 automatic weather stations in Greenland, so a very intense and in-depth knowledge of that wonderful island, and is a contributor to the IPCC assessment report and also lead author on the Arctic Monitor and Assessment Program. So I leave the floor to you.
Thanks a lot. It's great to be here to talk about the Copernicus Arctic Regional Reanalysis, CARA. Looks like my slides, if you can read that at the top somehow, the text got quite small. So the Copernicus Arctic Regional Reanalysis, CARA, it's adding value in our ability to monitor and report about climate as a complement to the Copernicus satellite data. It's adding spectacular detail that I'll show that I think can showcase Copernicus products in climate reporting, getting the news out to the public. And CARA also demonstrates the value of data assimilation. Next slide, please. So this shows the spectacular detail of the CARA data. This is a 2.5 kilometer grid that ingests a lot of observations, satellite data, ground data, and gives us this very detailed view. Here you can see a precipitation event around Greenland. Next slide. And by assimilating Copernicus Sentinel-3 data now since 2019, and this has been supported from a sequence of European Space Agency contracts and also the FP Cup program, we can transform the view of Greenland. You can see on the left from the ERA 5 data, which has a constant albedo for Greenland, to this hyper-realistic daily gap-filled albedo for Greenland, where you can see the dark bare ice area around the periphery. This is very important to assimilate these satellite observations into the analyses, because then the melt process is much more realistically represented, because albedo, the whiteness or darkness of the surface, determines most of the energy available for melting. Next. And we're also adding into Kara this network of stations that I've helped install and is now being taken forward by Denmark, 40 automatic weather stations. The assimilation of the pressure data especially dramatically improves the accuracy of the forecasts that compose the Copernicus Arctic Regional Reanalysis. These data begin in the mid-90s, and by the last 10 years, again, it's about 40 stations. So we have a jump forward in the accuracy and realism of this product around Greenland. Next. Just an example from one of the weather stations quite high in the southern Greenland ice sheet. Just last year, we're observing rainfall at almost 3,000 meters. This has happened again this year. We've had melting at the top of the Greenland ice sheet, and this is the type of extreme event that really captures the public's attention, and that can highlight the issue of amplifying climate warming in the Arctic. Next. This just shows the green areas where the Kara reanalysis provides a higher accuracy than the ERA 5 data that we know and love. Next slide. So I'll focus on an extreme event where you can see 30 meters per second onshore flow to southern Greenland. And what can that tell us? This is something that we're preparing to publish as part of a special issue, and really to draw attention to this new data set. Next slide. Zooming in, we can see the strong onshore flow halts abruptly as the air encounters the southern ice sheet. And that's part of the moisture dumping onto the ice. Next slide. I published about this last June, and these atmospheric rivers are coming into focus here using ERA 5 data among a lot of other observational data. Notice how this band of heat and moisture, what you're looking at is the total column water vapor. The red colors turn very blue when encountering the ice sheet. And again, this is part of this moisture that's really dumping onto the ice, along with a lot of heat. Next slide. And we are verifying both Kara and ERA 5 data using independent rain gauge data that we're putting on some of, and a growing number of these weather stations. But I'll just show you the results from this collection of first measurements we started in 2016. Next. And as you can read across from a number of regional climate models, starting with ERA 5, we have the correlation and then the average ratio between observations and models. And for the collection of data measurements here, we find a dry bias from ERA 5 at these locations. Japanese model has slightly less of a dry bias, a Belgian model, 2 Dutch models. And down at the bottom, we actually have agreement for rainfall and a higher correlation for this Kara Copernicus Arctic Regional Reanalysis. Next slide. Which gives us confidence to produce arguably the most accurate and detailed maps of, say, rainfall for Greenland. This is the rain fraction, and if you can see, it's a narrow band of yellow colors around the periphery of the ice. That's where half of the precipitation falls as rain. And this can deliver a tremendous heat flux to the ice. It can be part of strong melt episodes, and that's what we're using the CARA data to in a research capacity. Next. And one rainfall event extreme where there was more than 265 millimeters of rainfall onto the southern Greenland ice sheet there. We measured at the same time 300 millimeters in agreement with the CARA data. Imagine that, 30 centimeters of rainfall in a day onto ice. This is part of an increasing pattern of rainfall onto Greenland, and its interaction with the flow of ice is still a science frontier. So this study that we're preparing to publish, deadline next month, will add quite a lot of detail for the rainfall extremes. Next slide. These are vertical velocities, and there's a lot to see here with the red shape offshore of Greenland. This is a strong updraft, a bow echo that the CARA data resolves. The wind vectors turn to the left when actually the increase in the Coriolis effect should have them turning to the right. This is because of the barrier wind effect of the air flowing off of the flat ocean and encountering this elevated ice sheet. You'll see updrafts, downdrafts in the fjords, and most importantly for the rainfall during this event, you'll see some red colors on the southern ice sheet, and that's the uplift that's providing the cooling mechanism that leads to the strong rainfall in this event that we're studying in detail in this publication in preparation. Next slide. And just last August 2021, rainfall was witnessed at the upper elevations of the ice sheet. And here we are beginning to use the CARA data to understand the meteorology and thermodynamics of this event, where you can see the 0 degree isotherm is that isoline where you have temperatures well above melting over the southern ice sheet for the entire period. But this was it was a heat wave. It was an atmospheric river. We've learned quite a bit about this, and the CARA data will add a lot more variables to our ability to study events like this. For state of the climate reporting, so the various extremes, like there was a September melt extreme this year, the latest, strongest melt on record for Greenland. And if we are talking about 2022 Greenland in European state of the climate reporting, this September heat wave in Greenland would be arguably something worth mentioning as part of an increasing pattern of extreme climate events for Greenland and the Arctic. Next slide. And we've begun looking at the rainfall. This was the first time rainfall witnessed at the Greenland ice sheet, and we've captured it in several of our weather stations. Next slide. And I think this is my final slide, where also bringing these data to the public, we can showcase CARA, and because the public really does demand, they want to know what's happening. And we've had some success using social media and video to get the data off the computers and out into the public's attention, working with journalists and communicators to translate the science into information that is grabbing headlines around the world. And so here we can showcase the Copernicus products as this next generation high quality information. So it's great to be part of this, and thanks for the opportunity to present.
Thank you, Jason. Thank you very much. This is really fascinating, both as a climate scientist and as a sailor looking at this high resolution wind field. It's really very fascinating. Unfortunately, time is running, so we need to move on. There will be time for questions at the end. Thank you again, Jason. The next talk would be about snow monitoring, but it will be Michel Cherlet from the JRC giving the talk. He's a geographer and a soil scientist from University of Ghent in Belgium, and he works at Joint Research Center of the European Commission, where he coordinates the EU Copernicus Global Land Service. So without further ado, I leave the floor to you to talk about snow monitoring. Over to you.
Okay, thank you very much. Good afternoon. Okay, there comes. Okay, so I will tell you a little bit about very, very short, very condensed, something about the land monitoring service, the cryosphere products, snow and ice monitoring, and some other applications. Next one, please. So the Copernicus Land Monitoring Service provides information on land. We were more focused, let's say, traditionally on, let's say, the other parts of land and not so much in the northern or polar areas, but the data, of course, we have more and more data and we can extend also more and more north, and that's what we did. And so some of these products are very relevant, let's say, for monitoring snow cryosphere conditions, but also just land conditions. So we have products at the global scale. Next, please. I didn't know there was an animation here, sorry. The next one also. And then global, we go to the pan-European scale, and from there also local. The service is jointly implemented by the European Environment Agency and the Joint Research Center of the European Commission. Next one, please. So starting from, let's say, the European more point of view, we have a number of high resolution products because the area is a bit more condensed. And relevant products there are snow cover, snow properties, and ice cover. Snow cover is a fractional snow cover, persistent snow area. And these are products which are high resolution, 20 meter Sentinel-2 based, and are produced in NRT, near real time. That means also less than 12 hours after sensing. So that's a very quick provision of the data of the product, the final product. Snow properties, actually, it's a wet snow and dry snow. This is a mountain product. It's at the moment still over mountains because, I mean, there is a difficulty there in masking coherence issues in agricultural areas. But I'm sure this is done over the Alps at the moment, for instance, but I'm sure this information can also be probably derived in the future over interesting and relevant northern areas. Ice cover, river and lake ice extent, it's also at 20 meter within Europe, and you will see there is also a product at global scale in that. And river and lake ice, extent. Next one, please. At global scale, then we have relevant different products, lake ice extent as well, but it's, for instance, rivers are not included there because the resolution is much coarser. Here we're talking about 250 meter for a smaller area over the Baltic and 500 meter resolution over Northern Hemisphere. Same for snow cover extent. We cover a larger area at a daily scale, but at a coarser resolution. So 500 meter for Europe, 1 kilometer for the whole Northern Hemisphere. And for the snow water equivalent, which is then a product which is derived from coarse, very coarse data, and it's the unique information in this sense is a microwave and infrared data at 5 kilometer. These products go up to 85 degrees north. Next one, please. So here you see an example of this global or the Northern Hemisphere snow cover extent. On top, the more purple it is, the more percent of the pixel of the area observed is covered by snow. This is at the moment still derived from Moody's data, but we have in the pipeline, and it's in demonstration mode already, operational, the data, the product derived from the Sentinel-3 SLSTR sensor. And you see the smaller example underneath there, as well on the right, the example of the 20-meter pan-European snow cover extent with the same legend. Next one, please. On the bottom right, you see the lake ice extent for Northern Europe. This is this kind of Baltic area, which covers quite a number of lakes in this area. It's quite important for the region, this lake ice monitoring. It's at 250 meter, and we have a similar product at 500 meter for the Northern Hemisphere. Now on the top left, you see the snow water equivalent, and the snow water equivalent is actually a product which indicates the amount of liquid water which is in the snow. So when the snow would melt, how much water is left. And this is of course important for things like flood forecasting, water level monitoring for reservoirs of hydropower plants, for instance, also. You see on the image in the grayish area, the more white, the more water there is in the snow. Next one, please. So the application of that product, and I just give you a few examples here, is used for water resource management by, for instance, authorities in Finland. They use it over the Kemijoki watershed, which is the Kemijoki is the longest river in Finland with 500 kilometers more or less, and provides 2/3 of the Finnish hydropower capacity. On the image, you see on the left and right a difference between the modeling, let's say, the forecasting, the prediction system, when including the soil water equivalent and not. Okay, I must say, okay, it's the animation, it's not so clear, but I come back to another little graph a bit later. Next one, please. So again, here you see on the Kemijoki watershed, the example of including the snow water equivalent into the river discharge assimilation models. Now, if you look on the graphs, because the images show the animation, but the graphs are more visible, let's say, you see the blue line is the forecast in which the snow water equivalent is included. And this is very close to the gray line, which you hardly see because it's on top of it practically, which is derived from the pure observation, so the river gauges. And the forecast, which is the orange line without the soil water equivalent, has much more deviation, let's say, from the observation model. So it has a very positive effect in including this soil water equivalent data into the river discharge monitoring forecasts. Next one, please. Snow water equivalent is also, as I said, important for monitoring the water reservoir levels and the assimilation of the inflow forecasting. This is used, for instance, in Sweden, Finland, Sweden by the Swedish Meteorological and Hydrological Institute. They run this hydrological model for it. Finland has the hydrological operation and prediction system, which we have just seen. And also they use the Environment Institute for the water simulation and forecasting system. Also large hydropower operators in Scandinavia, and you see the two names there on the lower left, they are relying on the snow water equivalent for monitoring and forecasting their hydropower operations in Scandinavia. And again, we see that the model's information, including assimilating the soil water equivalent information, is much more accurate than without. Next one, please. Similarly, there is this model I have told you about before, the SAR wet snow. It's a European product, and it's only derived over mountains areas, but thanks to its high resolution, there is the possibility to derive the slope and aspect and the height of the snow and the wet snow cover. So that's very important, again, for flood forecasting, for river flow and melting, of course, and for instance, also avalanche prediction. As I said, this product is only over mountains in Central Europe at the moment, but most probably this can also be extended over where there is, of course, topography, relevant topography over northern areas. Next one, please. The high-resolution information on ice on rivers and lakes. You have seen an example of the global data set, which is much more coarse and covers only the bigger lakes. This European-wide product on high resolution covers also rivers. And this is, of course, an important information in northern rivers on the navigation possibilities and so on. So here you see the images which have some blue on it, means and you see the legend there. The dark blue is still open water. The cyan blue is snow-covered or snow-free ice. So that's rivers which are covered with ice. And so this information in near real time gives possibilities of monitoring the navigability of the rivers, for instance, and also the status in general of the river. Next one, please. This is the information which you can get on the system of the data. So you get information on water cover. There are some statistics within certain hydro segments, which are well-defined segments of interest. There are these APIs access for near real-time services. We have seen there is also a Jupyter Notebook application for that, for access of the data. Next one, please. And then I come to another application which is more on land and more related to animals and people, let's say. It's a system, an innovative system which was set up to monitor animals. It's owned by one of our contractors, which is CLS. And in these northern areas, the normal traditional herd management has come a bit to a limit, also because of the changing environment and the rapid differences there. So there is a need for sustainable herding, for knowledge on replenishing the genetic stocks and also the food stocks, and to identify vulnerability and the threats of the herd, for instance. So the herder would need information on near real time on the localization of the herds, on the health and disease situation of the animals, and also on the status of the habitat. Where is the next water point? What is the status? Do they like it? Do they not? Are there other herds in the areas or not? Next one, please. And here we see the setup of the system. So the small herding system depends on 4 space systems, basically. And I just named them all. One is the navigation system, which allows the animals which wear a collar to track them. This information is sent through the SATCOM services to the system to include it in the models. The herders and the management people get the access to the data by telecommunication. They can also upload information, and the background information, if you want, in the system is habitat mapping and vegetation status, in which then, and you see the red circle there around the box, which is the Copernicus data, which comes in at that moment into the system. On the top right, you see a tracking of reindeers in these areas. Unfortunately, the testing and setup of the system was done over the northern Russian area, so that the war, of course, will have its effect now on the further evolution of that. But also this type of information, this type of management, this type of monitoring can also be set up for other animals, such as penguins or migrating birds, for instance. Next one, please. And the Copernicus data, which is useful for this, is, for instance, vegetation-related information, such as the FAPAR and the NDVI, which are vegetation indices. We cover now up to 85 degrees north. We also have land cover information, mapping snow or no snow as a class, but also then, of course, shrubs and mosses and things like that as classes. And this goes nearly up to 80. And that's, of course, because mainly it's based on visible data, and we need a track even tracking possibility throughout the year, and then the lack of winter season in the north, the lack of visible light is then of course impediments the calculation of the variable. So that's in a nutshell the a little bit of a reconnaissance of the globe of the lens surface and a few products which are relevant for polar monitoring. And of course, we, in that sense, are starting to collaborate and with the new hub and providing this information and applications. Next one, thank you very much for the opportunity to present. Thank you.
Thank you. Thank you for the very interesting talks, and especially this last slide about the migration of animals. I think it resonated with many in our audience. So thank you for that. We are roughly running at 10-15 minutes late, mostly because of the technical issue we had at the beginning. Apologies for that. I suggest we keep the schedule as it is and go rapidly to our last speaker of this session before our Q&A and the coffee break. So our next speaker is Annette Barge, who will be talking about the permafrost thawing. So Annette got a PhD in geography from the University of Reading before moving to Vienna and getting her venia docendi in applied remote sensing there in 2011. In 2017, she founded BGEOS, an Earth observation company with a focus on R&D located in Austria. So the focus is really on permafrost, which is probably one of the most important topics when talking about climate change in the polar area. So I leave the floor to Annette. The floor is yours.
Thank you. So I am the science lead of the ESA Permafrost CCI project, and I'm also involved in the Horizon 2020 project Nunatayuk. And I will show you some highlights from both projects in this presentation. Next. So permafrost monitoring is quite challenging because permafrost is a subsurface phenomenon. We cannot see this directly from using satellite data. So we have to involve some modeling. So compared to sea ice, or at least sea ice extent, it's quite challenging. So what you see here is a representation of permafrost extent from 1997, as well as sea ice extent. Next slide. Yeah, so here, and this is now 2019. And most likely you have been, now you saw or you're aware of this change in sea ice, which is quite prominent. But for the permafrost, that's more difficult to see. But there are actually changes all around the Arctic along the boundaries of permafrost. So now focus more try to look more on the boundaries of the permafrost. Next. So that has been jumping back to 97. And now next. So this is now in 2019. So actually this shrinking is happening across the entire Arctic. Overall, more than about 25% of the Northern Hemisphere is affected by permafrost. We have these, what we call continuous permafrost, the dark blue areas here, and then the transition zone. And there are quite a large, big changes in this transition zone. Next. But it's not only at the boundaries where we should look at. We also need to, look into the temperatures itself, how they are changing. And the biggest changes are happening near the Arctic coastline in the high latitudes, and specifically at those coastlines which are in the proximity of the area where the sea ice minimum is declining most. Yeah, so that's where these red areas are. And so what we have here represented is the change at the 2-meter depth for an approximately 20-year time series. And 2-meter depth is usually what we are using for permafrost extent, or when discussing permafrost degradation. But the CCI service, permafrost service, we offer temperatures at the surface, 1 meter depth, 2 meter depth, 3 meter, 5, and 10 meter depth ground temperature. Next. So just coming back to this sea ice connection. So this is a sea ice record that you probably, a sea ice extent record that you may have seen many times before. So we have the decline of minimum sea ice extent. And next. And this is now the representation, the average of the time series produced in permafrost CCI for the Northern Hemisphere permafrost extent. And you see at the same time where minimum sea ice extent is declining, ground temperatures are increasing. And for the permafrost area within this 20-year period, the temperatures have been increasing by, on average, about 1 degree Celsius. And it's there's quite a high correlation actually with a linkage here to the sea ice extent. So we see opposing. So where we have when we have a year with a strong decline in the extent of sea ice, minimum we have a strong increase in ground temperatures, specifically along the coast. Next. Here, this is a representation, or I've split this trend up into regions and we see a similar trend all around the Arctic. It's for Greenland, Alaska, Canada, Russia. And this corresponds to what we can see in the boreholes, so what the in situ data show us here. So we see this increasing temperatures all across the Arctic. At the moment, the status of the CCI is that, well, at the moment we have not yet integrated the Sentinel products, but that's going to happen in the next phase and most likely within the next year, that Sentinel 1.2 for soil characterization, land cover characterization, and Sentinel-3 for the land surface temperatures will be integrated. And and also snow services. We are here depending on other CCI project services. That's CCI land surface temperature and CCI snow. And that's this upgraded version is what we hoped that we can provide to projects like Arctic Passion. Next. So, but what is the big issue here is for the Arctic with the thaw is we have a lot of carbon in the ground, and almost all over the region where we have permafrost. Next. And specifically what is of interest here is what is happening within what we call the active layer. So the upper few centimeters, decimeters to meters of the land surface. So the active layer thickness is deepening, what means that more carbon stored in the ground is becoming available for decomposition by microbes. And this thickness of the active layer is increasing across the entire Arctic. And on average, it's increasing by has been by 2.5 centimeter during from 2007 to 2016. So this is, I thought we do not see this strong temperature increase in the permafrost, in the ground itself. We have at the same time, well, we have this increase of the active layer, and material in the soil is becoming available for decomposition. I thought there is still permafrost below. So there's also a further product in the permafrost CCI, which is the active layer thickness. And that's together with the other data sets that's available from the CEDAR archive. Next. So loss of carbon is one big issue. Then what, unfortunately, I don't have time to show this, but there is specifically Sentinel-1-2 is used a lot to identify changes at the land surface, which are result or connect to permafrost thaw, that's land cover change, thaw slumps, terrain change, Sentinel-1 being used here is very important. And this overall change or this ground stability, this is something what affects people living in the Arctic. Before I come to that, I just want to mention the AMPAC initiative. That's a joint NASA-ESA initiative, the Arctic Methane and Permafrost Challenge. And within this initiative, it specifically will look at products coming from Sentinel-1, Sentinel-2, which help upscaling methane fluxes from in connection to permafrost thaw. So next. So now coming to people living in the Arctic, next. So within the Horizon 2020 project Nunatak, we have been looking at specifically impacts or potential impacts on people living near the coast regions, and focusing on an area that's here represented 100-kilometer buffer distance from the coastline, and used processed Sentinel-1 and Sentinel-2 for this entire region, the entire Arctic, at a resolution of 10 meter. So what you see represented here, these hexagons, is just an aggregation of the actual data set, showing us that wherever there's a hexagon, there are people living, and or there is some impact. It's oil and gas industry, mining, military presence, and by combination with time series, other Landsat, we identified at least 15% of this human impacted area is new after 2000. And all these, and about 50% of these infrastructure, human impacted areas currently on permafrost, will be, there will be no permafrost anymore by 2050. So if I say no permafrost, that means no, or temperatures above 0 degrees Celsius at 2 meter depth. So 50% of this is currently infrastructure on permafrost. Next. So there is quite a substantial added value of satellite data, specifically Copernicus data, for monitoring permafrost or impacts of thaw, or identifying assets are vulnerable to in this context. So with thawing ground itself, land surface temperature is crucial. Also land cover information and snow for parametrization of heat conductivity of the models. Terrain change is of high importance, Sentinel-1 here. And yeah, and then this expanding use of the Arctic is something what needs to be considered. And here the availability of Sentinel-1 and Sentinel-2 brought us quite a big step forward. Due to the spatial resolution with the 10 meter and in combination with machine learning and artificial intelligence. So we have developed here in this Horizon 2020 Nunatak project a new type of product for the Arctic. Yeah, that's all for permafrost. A very short overview on permafrost.
Thank you, Annette. That was brilliant. Thank you very much. As I was saying, we are running a bit late, but I don't want to squeeze our coffee break, also because in the afternoon we want to be fresh and well rich in caffeine to follow the discussion. But before getting to the coffee break, I would like to open up to some of the questions. As you know, we have the Slido. We have not been particularly, or you have not been particularly active in the Slido yet. Now there are some polls open as well as questions, but I would like to to go back to the speakers. I would like them to switch on the camera again, and I would like to ask all of them one question with the desire of being short in their answer and to the point. My question is, and it was very clear in the presentation from Annette, on the gaps in the observing system. So if it were for you, what sort of measurement would you like to see done in the Arctic more? What sort of information is missing? So if you can suggest one and the reason for it, that would be brilliant. Any take here? Go, Annette.
Yeah, so I didn't show much results. It's on the Sentinel-1, Sentinel-2, specifically regarding Sentinel terrain change. One big challenge that there is, or one issue that there's no circumpolar product for these time series, is that there are no consistent acquisitions of Sentinel-1 for the land area of the Arctic. It's regarding mode and gap. At the moment, since now that Sentinel-2B is down, there are no acquisitions anymore at all. So we haven't seen acquisitions here. And this is now interrupting many time series of where we monitor the permafrost thaw impact. So that's quite a challenge, these inconsistent acquisitions.
And if I may, just a follow-on question, do you think, going back to the presentation of Jason about the Arctic reanalysis, do you think that the reanalysis, or anyway information from satellite that is mediated by a model, can play a role in filling some of these observational gaps?
Not for terrain change. These reanalysis data are very crucial for the permafrost modeling. So we are actually combining, it's not purely land surface temperature. There are many gaps due to the clouds. And we are using reanalysis data to fill these gaps. And it's really crucial that these data are, that they are really precise. So at the moment we are using, we're doing a bias correction of the reanalysis data because it is known that they do not really fit. So we do some pre-processing to make them fit with the land surface temperature. But any improvements of the reanalysis data are really are very, very helpful for the permafrost.
Thank you very much. Karina, maybe you want to intervene? I don't see you, so if you want to intervene, please switch on the camera.
Yeah.
Please.
Thanks. Yes, in terms of for the ocean, I have one specific remark, also link this expertise as mentioned earlier. The Arctic is affected, amplified also from climate change, but also hosting climate tipping points. And there are specific sensitivities with climate linked to the ocean and cryosphere aspects. And so measurements of the subsurface ocean, in particular for the hydrographic, but also for the impact on the ecosystems, are urgently needed in order to either complete the interaction from a warming ocean, but also the implications for an acidification and the implications for the ecosystems. So it's from my side for both the Arctic, but also the Antarctic area in terms of subsurface temperature, particular temperature, but also other biogeochemical and biological parameters.
Thank you. Thank you very much. I don't know whether any of the other speakers want to intervene on this point. I don't see. Michel.
I fully agree also with Annette on the S1 acquisitions over land. I mean, that's something we also see in other areas, by the way, also. We have our soil moisture, soil water index products, and they are fully derived from Sentinel-1 data. And yeah, in these areas, this is still lacking. On the other hand, I think we have from our side, I think we have more or less enough observations. It's just like from a land surface, I think we have to and this we will do probably through the hub, then a little bit more focus on the Arctic areas, because traditionally, let's say, land applications are not so much looking at Arctic areas. And I think if we move our focus a little bit to there, I think we can come up with quite a number of reusable products there.
Thank you. Thank you very much. I don't see other people on. So if there are other speakers who want to respond to the question or make comment, just switch on the camera. Otherwise, I will assume you're okay, and we can move to the coffee. Just I'll leave maybe a few seconds for you to react. Okay. Then before leaving for coffee, I just want to mention that there are a couple of polls in the Slido, so you can go there and respond to some question, and we'll use the response to this question as a talking point for the next session. We are a bit late, as I was mentioning. I would suggest to keep the coffee break short, but within a reasonable limit, and come back here at 3:45. Central European time. So in slightly less than 10 minutes. Enjoy your coffee and speak with you later.